why liposomes are really belong to the field of nanotechnology. One, because nature make it so. And why nature make it so? It's because this kind of, by default, that particle below 100 nanometer can take advantage of the EPR, and if they are above it, they can do it less, and if they are 500, they cannot do it at all. So we have here a filter that decides for us. The other are really nanotechnology reasons. Is we have use a bottom-up approach for the fabrication. There are self-repaired systems. The lipid bilayer is very small, only a 5 nanometer dimension. We have nanovolume, which give us a lot of advantages in getting very high loading in a very controlled release, which I'm going to show you in a little while. They are very different from nanoparticle in their toxicology, which means they are much less toxic than all other systems, and they are biocompatible, and you can find it all there. I don't have time to talk about it. This is a kind of a concept map that every student that or worker in my lab get when he starts developing a system. And that's actually what you have to do. First of all, you can see it's a very multidisciplinary nature. You have to know a lot of things and collaborate with a lot of people. The second is you have to make a decision if it's worth to do all this, namely if the benefit that you will gain, if you succeed to reach a system, will be good enough that someone will decide to invest in you enough money to do the development of this system. Many of the things, if you look for the answer will be no, and then you look for another system. If your answer is yes, then what you have to do is, one is the engineering of the liposome, contain many, many parameters, and building all the biological models, the cancer model or inflammation model or whatever, doing biodistribution and pharmacokinetic, efficacy, toxicity, getting therapeutic index. If it's good enough, you can apply for IND, for a clinical trial, and then the money starts, of course, to flow. You need a lot of money for this. Now, even if you did well and you have a very good CMC, still it doesn't mean that you are there, because there is a very large difference between the animal and the human. And I want to point only to one difference that costs us a lot of money and a lot of time, and that's a difference in size. Mice are very small, they have a very small blood volume, and humans are very large and have a very large volume. The difference is 3,500-fold in the blood volume. So when you inject a drug, even a small amount in liposome, into the blood, the dilution pressure on this liposome is very, very small, and the drug will be retained with the liposome, and you get a fantastic result. We cleared in my life probably millions of mice. But if you do it in a human, that's not the case. The dilution is so big, and if the drug is not held well, partition coefficients are not good enough, all the drug will leak, and your liposome are really meaningless. So this lesson is very important to remember. Now, to get successful, you have to overcome 3 barriers. You need a stable and high enough loading of the drug. You need a steric barrier to prevent interaction with the blood component, so the circulation time will be long enough, and you need a small size to extravasate. You have to remember that the loading of some drug is quite big. For example, doxorubicin, 50 milligram per meter square. You're giving every human being 100 milligram of doxorubicin. You need quite a lot of liposome of this if you don't do the right loading. So you can, based on this, make a decision if it's worthwhile or not. Let me introduce you to Doxil. This is the Doxil, this is the vial. If you take this vial, every ml of this vial contains 2.3 10 in 14 particles of liposome. Every particle contains 10,000 molecules of doxorubicin. If you look carefully with the cryotransmission electron microscopy, you can see the crystals of the drug inside. It's a kind of a reversible crystallization due to the loading method that I'll tell you in a little while about. And you can see the structure, and 98% of the drug are in this precipitate. That's the cartoon of it. You can see the peg, which is really on both sides. This is the steric barrier we use. I'm not going to tell you about doxorubicin. It's one of the most potent drugs and I think it's very useful. I mean, what I'm very proud of is that actually we know now what every part, every small part of this liposome is responsible for. We know what's the PEG doing, we know what's the bilayer doing, we know what's the crystallization of the drug doing and the free drug doing. So we have a full control over the system. And I think because of this, we were successful with Doxil. So I have to go through some core technology, the loading techniques. We use a gradient. It's a bioenergetic principle in which you take some ion gradient, in which one of the ions can leak out, and this is the ammonium. When the ammonium leak out, it's a very hydrophobic gas, so it can leak out in a neutral form. It leaves behind proton and sulfate. And now you have a very hungry liposome. They have to get something in order to come back to peace with themselves. So what happened is when you put amphipathic weak base inside, in the solution, the liposome will suck it in, basically. The liposome will suck it in, and then it will be protonated, get the sulfate, and precipitate this crystal that you saw inside that we also studied by X-ray. We developed a mirror image for amphipathic weak acid, and this we use for some steroids very successfully, going now to clinical trial, but I don't have a laser. I have to bring one. Anyway, so this gradient is what the FDA liked very much, one of the things he liked very much about the project. Now we have to decide about drug, which drug to select. So the method we use then is a very simplified method, looking by partition coefficient, and based on this we selected the best, the drugs that we fit best to be loaded by this method, and doxorubicin worked very well. But now we are much more sophisticated. I have some student that can deal much more better with computational biology, and I myself took some courses in this. So now we do a computation biology on this, and based on a data bank of 9 drugs that we work in the lab for the last 25 years, we develop a model that based on this we can make a much better prediction about the loading, much more accurate. And you can see, for example, this is for some of the steroids. We can select the best condition. It's a WECA tree, decision tree that you can, based on the model, and based on this, you see some point, you go through this trip, and I don't have time to go through it, and based on this, you can I don't know why it doesn't move. So once we decided which drug will be good, and I'll show you some more, then we have to look for the lipid, and very important to know phase diagram of the lipids. And lipid has few phases. The best phase for us is the lipid order phase. This is a phase in which you have a lipid with high melting point together with cholesterol. This is not temperature sensitive, and it will enable us to get a very controlled zero-order release of the drug out of the liposome, which we want very much. And we try to keep ourselves very careful not to be in this region at all. So we are all the time at this region. And the lipid we selected, you'll see in a minute, are hydrogenated soy PC, a very cheap lipid from soy, that actually give us a lot of benefits. It has a drug master file, and the phase transition of it is about 53 degrees. Cholesterol, which lower the free volume and really enable us also to get the zero order release rate that we want, and the steric barrier, the PEG DSP. These are the components, here are the properties, and that's the way the bilayer look. If you look for high dimension, this will be the bilayer we are working on. These are the bilayer we are working with, and this is a bilayer that we work for other reasons that have a lot of free volume because of the unsaturated lipid here.